Thank you. Well, welcome. And for those who are grabbing lunch, feel free to grab a bite and find a seat. But thank you for having us today. As my colleague here introduced, I'm Alex. I'm the head of product at a company called Q-CTRL. So we build infrastructure solutions for quantum computers to make them useful and to help you get the right answer. Hope you've also enjoyed some of our previous talks by our company earlier in the conference. So yesterday, our founder and CEO gave a keynote talk about our premier flagship product called FireOpal that was launched. And then the day before, our chief strategy officer, Arvind, spoke with a few of our collaborators and partners about the benefits that they've experienced from some of our products and how they're incorporating it into our business. So I hope you've been able to catch those sessions. I'm really delighted to put a spotlight on our guest speakers here today. Before I do that, I just want to quickly go into what we do at Q-CTRL. So we often say that our mission is to make quantum computers and quantum technology useful. And so as you may have heard, we released our flagship product called FireOpal just earlier this week. So it's free to use, available to the public. Anyone can access it, download the Python package, and immediately bring their quantum algorithms, submit their quantum algorithms to a quantum computer and get the right answer while saving time and resources. And again, as I mentioned, it's free to use. We invite all developers out there to start using it and trying it out. And as a product person, I'm especially excited because not only are we as a company trying to make quantum technology useful, with this product, with FireOpal, we are also making it accessible and also increasing developers' agency to be able to continue to build algorithms and realize the gains and the impact that these algorithms can bring. And just to give you an example of this, you may have seen this in some of the previous talks, but again, take Grover's search, needle in the haystack problem. Today, when you bring this algorithm to any other quantum hardware that's available, typically what you see is on the bottom left. You typically get randomized output. And whereas you should be experiencing what you see on the top left, you know what the ideal solution is, but what you get out is randomized output. With FireOpal, which is, again, super easy to use, a single line of execution where you submit your Grover search algorithm, you get the right answer. So you can see through numerous tests that we have had, we continue to show that over the probability distribution, you can get up to 1,000 times improvement in accuracy. So that's why we are so excited about releasing this product to the public for other developers to try out other algorithms that they want to test out. And in fact, this is a good segue to our first speaker, Alex, who had done his research at Xerox PARC, and he will go into some of the research and some of the algorithms that he tested. And in fact, we had tested this with several other algorithm developers and researchers across a lot of different institutions and companies before we actually released this to really validate the capabilities, understand what the gains were. And so Alex, I'll invite him up to stay up on the stage, but I'll let him dive into some of the work that he did in their use with FireOpal. So join me in welcoming Alex.
Thank you. So, enough marketing for the day. Thank you very much, Alex. It's very delightful to be here. I see many friendly faces. For the record, I'm not paid by Quantum Control, so all the good stuff that you're going to hear about them, it's from my heart and from my mind. It's not like I don't make money for saying good stuff. Now, to introduce a little bit what we have done, and it was a very interesting and very practical experiment, I will start by sharing my interest. I come from computer science, combinatorial optimization. And like many years ago, I was studying model-based diagnostics of Boolean circuits. And of course, I was designing algorithms for that, and some benchmarks came out, and then for some reason, those problems from model-based diagnosis, they turned out to be very interesting from the standpoint of benchmarking quantum devices. So I want to be a little bit harsh here. There are many of you providing quantum solutions. Only one is going to win at some point. So there must be an objective truth of what's the fastest algorithm, what's the fastest approach, what's the biggest circuit we can solve. And from experience, coming up with a proper comparison is fantastically difficult. Assessing the role of various tools is fantastically difficult. We are all engineers and scientists here. We want to talk about not only about quantum number of qubits or quantum volume or circuit depth. We want to be better than that. And I hope that after I finish with my 10 minutes here, that you will all be a little bit more grounded in terms of benchmarks, in terms of experiments. We'll be talking more precisely. We'll be considering, as a computer scientist, everything for me is is some trade-off. So you have to say what you're giving, in terms of energy, and what you're gaining in terms of accuracy, and then we can make our business decisions based on those benchmark results. So if you guys are from business and if you're paying money, you have to know exactly what you're paying for. So I'm very interested in diagnostics, in scheduling, in logistics, in theorem proving, in circuit design, in model checking, and so on. How can we use quantum devices, and how can we use optimization, error correction and calibration, advanced calibration, software and hardware for improving the results. Let me share the results of this experiment that we did with quantum control. So a very quick introduction to circuit diagnosis. It's a bit of an esoteric problem that you probably haven't seen. You have a Boolean circuit, like a 1-bit adder, but of course we're interested in reasoning about circuits with hundreds of thousands of gates, similar to ones that you have in your mobile phones or your computers, and then you can ask me after the talk, what's this good for, and I can build the argument, but I'm not going to do this right now. So in this illustrative example, you have a small circuit having 5 gates, 2 AND gates, 2 exclusive OR gates, and an OR gate. It's all American notation. Then you are given some inputs and outputs. So the inputs and outputs are Boolean numbers, values, true and false, or 0 or 1, or whatever you want to make out of that. So you have something on the input and you have something on the output. The output is not what it's supposed to be from the semantics of this circuit. And you're trying to figure out what happened. This is the high-level problem of diagnosis. What could be an explanation of a mismatched output? Can be a short circuit, or one gate is behaving like another gate, and so on. This is a very difficult problem. I will not go into theoretical considerations here because this is not the right venue, this is not the right place. But there have been papers and papers. It's very close to satisfiability. It has certain variations of the problem are in the upper complexity and so on. So there are sigma 2 problems and so on. What I want you to pay attention here is that figuring out for a certain situation, for a certain observation, for certain inputs and outputs, you can have multiple explanations. So you can have an exponential number of them, exponential as a function of the number of gates. So here you have 5 gates. If every output can be stuck at 0 or stuck at 1, you have all possible combinations, so you have 32 possible explanations. For a circuit with 1,000 gates, you would have 2 to the power of 1,000 possible diagnoses. So not all of them, of course, are happening all the time, and that's what you're trying to do. You're trying to compute all possible diagnoses so you can explain the behavior of a system. Now, that's where the magic comes. we can either reduce this to another problem, something like satisfiability or maxat, and we can run it on the D-Wave machine, or we can reduce this to a quantum circuit, put all the diagnoses in a superposition, and then we can solve that. And this is super interesting because we can compare the performance. Let me talk a little bit about putting all diagnoses in superposition. You have to construct an oracle. The oracle for the fault model of the full adder, which was shown in the previous slide, is shown on the right for illustrative purposes. Then the superposition is done by the Hadamard gates in the upper left corner of the slide. Then you run the whole thing like multiple times, and you construct like a probability distribution function. And I want to contrast the algorithm here from algorithms like Grover or Shor algorithms. The PDF, the algorithm is such that it does not expose this kind of a threshold behavior, this kind of a majority voting behavior. So there is no error correction built in the algorithm itself, unlike the Shor algorithm where you have the error correction in a magic way in the semantics of the quantum algorithm itself. Actually, it's a hybrid algorithm, it's not a quantum algorithm. So this is like a new class of, so to say, algorithms where the accuracy and the error correction of the device and the stack actually matters. And then to compare the quality of any approach for solving those problems, you have to take into consideration not only the energy spent for solving this problem for computing all the diagnoses, but you also have to take into consideration the quality of the result. That's what I'm trying to make a case here. So in this experiment that you can read about, there is an academic paper about that. I mean, you can find it from me or from Alex Shih. We compared solving a benchmark, which benchmark is also available, so you can run it on your devices that you're building. If you need help in running it, we can provide this help. We ran it, and we didn't care about the energy because it's close to theoretical minimum, but we compare the output of output quality, so the quality of the PDF. We brute forced with classical compilation methods that we are going over in a paper, but I'm not going to bother you with right now. So we solved on a cluster some circuits. We solved this with IBM. We solved it with FireOpal, which is, from my naive understanding, a way to calibrate the gates and get better PDFs from every reading. And we compared the Hellinger distances to simulation, to analytical solutions, and there are no analytical solutions to brute force solutions on classical computers, to simulation, quantum simulation. We compared it to IBM, and we compared it to IBM with FireOpal. And what matters here is that FireOpal gave us an advantage. The quality of the PDF is 5 times better, whatever that number means. We can go into details in the paper and all that, but this is significant. This is the Hellinger fidelity that we improved. So the solutions of the IBM plus FireOpal is 4 times 66 times closer to the ground truth. That this was my biggest concern than IBM. We can have relatively non-trivial circuits, more than 10, something made out of about 7-8 Boolean gates. So the mapping to quantum circuit is relatively economical. This is important. And actually, based on that, I just want to conclude that there are many interesting problems in combinatorial optimization that should be solved with quantum computers. Cryptography is not interesting, diagnostics is, logistics is, go for that, use our benchmark, talk with us, like in the hallways, me or Alex Shih, we're going to compare, try to improve. Thank you everybody.
Thank you, Alex. Yeah, thank you very much. Yeah, definitely stop by if you have any questions. We can send you the paper, send you the benchmarks. For our next speaker, I'd love to introduce Dr. Wojciech Burkot. and this was in collaboration with their team at BEIT. And we're excited. They've been one of the earliest users of Fire Opal, who have, again, as I mentioned, who have helped us, given us feedback, and has stress tested this product before we got to this point where we are releasing it to the public. So I'm really excited about some of the work that they've done, as well as some of the software capabilities that they've applied on top of Fire Opal to enhance the amount of gains that you can get. So please join me in welcoming Dr. Wojciech.
I'm not me here. I'm just pretending. The work has been done by Janek Tułowiecki, our software engineer, with collaboration with Q-CTRL guys, so I'm just presenting. And the first few words will be about BEIT. BEIT ambition is to become #1 quantum software independent quantum software IP provider in the whole world. It sounds very ambitious for the company of 16 people, but if you go to the recently published reports, we are between 45 and 49 in holding patents in quantum technologies. If you reduce that just to software, we are in top 10 already. Yes, I know it doesn't cut it, but we are aiming at this #1. The other thing we do, we are trying to find a relevant IP. It's not frivolous. We are trying to search for the areas where you can expect quantum advantage, and then find solutions which are relevant in that area. I just hate hype around quantum, which resembles well-known business model where you are doing something at a very small scale, then you have 3 question marks, and then you profit. You need to know how to move from the small-scale experiment to the actual business size of a problem. So one of those areas is Grover search. It's essentially a needle in the haystack problem. Classically, if you are returning the needle where it was, you need to run this something like n times to find. Quantumly, square root of n suffices. But in fact, up till very recently, the time complexity of the Grover search was square root of n times log of n. And what we managed to, here's a redefinition of the problem. So what we managed to do was actually find a theoretical solution and drop this log term, which gives us between now, small scale machines, to quantum advantage at something like 200 qubits, which give us something like the additional factor of 3.6 of the advantage without any work. It's done just in this paper. It was hard work, but very clearly worth it. So we are trying to go after hardware manufacturers and convince them that we can actually show that their machine is world best. It's very hard because of the necessary circuit depth to run Grover search in its original version on any hardware, even if you have as few as 16 states. So imagine 4 qubits, and you are trying to find one of 16 states, and it is already hard because the circuit depth is such that the computer gives you just the random noise. So here, besides this theoretical work, we are doing yet another thing. We are doing optimal decomposition of large multi-control gates into the native sets. This gives only a polynomial, or actually linear, speed up, but combined with every other factor, it's something which is of value. So directly to the results. As I said, it's impossible to run the proper Grover search on even 4-qubit machine. We did that actually in 2020 and presented the results here, pitching Honeywell against IBM, so to give us access to their machines and showing that IBM is the best superconducting quantum computing machine, while Honeywell is the best ion trap machine, having the benchmarked by the Grover search. Here are some results which are beating this and done with the help of FireOpal. So classical random sampling gives the theoretical probability of 1.5 something on a single iteration. You cannot fit many more iterations there. If you supplement Grover with FireOpal, here is one caveat. The FireOpal said they are working in the control layer, shaping pulses and stuff. But if you look at the numbers, it's very clear that they are touching the gate definition as well, which actually Michael alluded to yesterday as well. So the number of the gates for that same problem with FireOpal is smaller than the naive implementation. But then if you go to our implementation, we are essentially cutting this by half. So, and what that means, we are far away from T1, T2 limits, and you can do much better in using FireOpal to control the errors because they have space for that. It's very interesting. With that number, we could actually run 2 iterations, but it wouldn't do any good. It would be so close to the limit that trying to use FireOpal on that will just blow up and you will not get much better result than the direct usage. We did the same thing, and as you can see, we are getting, the consequence of that is that the theoretical probability here is pretty low compared to the maximum for the Groover, but it's still, as I said, it's still worth it. We did the same thing for 7-qubit search on Guadalupe, and again, our probability and small number of gates is significantly lower than what you will get with just naive implementation. Seems stupid. However, in fact, it is not, because that's the result. If you implement just row Grover, here is the solution probability. If you use Grover with FireOpal, not really leaving much space for their improvements, you are getting an improvement, but it's not really significant. But if you use BEIT with FireOpal, despite the fact that we are starting with a theoretical probability of something like 50% less than the theoretical maximum, you are getting significantly better results. So 7-qubit search on your left-hand side, 6-qubit search on your right-hand side. The improvement is, the guys were claiming the 11 times and more improvement, but this software is pushing hardware to the limit. You cannot do any better. We are extracting every single bit of processing power from those machines. So that improvement cannot be that high, but it is still significant. For 7 qubits, it's 2.1 times. For 6 qubits, it's 2.6 times. And if you think about the information gain, how much information are you extracting using those techniques, we are getting up to 11 times for the 7-qubit search. And it's obvious to say that this is currently the world best result in the unstructured search.